Chapter 3. We're looking at section 3.4, and our goals relating the first derivative test, this time to the second derivative, though. What does that mean? And we're going to find these things that are going to be called inflection points. So what are inflection points? Here's your definition. I already wrote it out. Points on the graph where concavity changes. Points of inflection. Places, specific points on a graph where concavity changes. Now, sometimes concavity will change at values that don't exist. It might change at an asymptote. It might change things like that, be different on one side than it is on the other. But in order for it to be an inflection point, the function actually has to exist at the place where it changes. So points of inflection, we'll get to that, and intervals of concavity. Concavity, the difference between a function that's concave up and concave down. The way I think of it is if a function is concave up, that would mean if I continued down, I could make a letter U out of it. If it's concave down, then I certainly couldn't. So concavity, what kind of a bend in the line do we have? So first off, first goal, we're trying to relate this first derivative test to all this. So if we look at what we have going here, if my first derivative is greater than 0, what do we know? If first derivative is greater than 0, my function increases. If my first derivative is less than 0 for an interval, then my function decreases. If my function's derivative is equal to 0 for an interval, then my function is constant on that interval. And how often does that happen? We haven't seen very many times when that's taken place. Well, now let's make a comparison. Well, what happens if my second derivative is greater than 0? If my second derivative is greater than 0, what do we know? If my second derivative is greater than 0, then my first derivative increases. If my second derivative is less than 0, my first derivative decreases. If my second derivative is equal to 0 over a period of time, my first derivative is constant. Well, here's another connection that we can make. If my second derivative is greater than 0, if my second derivative is positive, it tells me that my first derivative is increasing, but it also tells me that my original function is concave up. On that interval. If my second derivative is positive, that tells me in that interval my original function is concave upward. If my second derivative is less than 0 in an interval or is negative, my original function is concave down, concave downward. And if my second derivative is equal to 0 over an interval, if my second derivative is equal to 0 for an interval, that means that my original function is linear. That means I'm talking about some sort of a line for my function. It doesn't have any concavity, which means it would have to be a linear function. So what's our conclusion that we're trying to draw? Second derivative. So my second derivative gives the same information. Second derivative gives the same information about the first derivative that the first derivative gives about the original function. So the connection is everything that we've learned about this first derivative test, about when the first derivative is positive, my function's increasing. Well, now all I have to do is change the wording. If my second derivative is positive, my first derivative is increasing. But we're also going to get a little bonus because if my second derivative is positive, that's going to tell me what kind of a bend I have in the graph of that original function. So kind of putting all this together, for my function to increase, for f of x to increase, if fx is supposed to be increasing, then I need to know that my first derivative is positive. F prime has to be greater than 0. For my derivative to increase, my second derivative has to be greater than 0. For my original function to decrease, f prime has to be less than 0. For my first derivative to decrease, f double prime has to be less than 0. So that little box right there is a pretty good little summary thing for us to keep going back and referring to. And I'm going to encourage you to kind of work your way back to that a few times, especially as we look at some of these examples. So there's your first goals, relating them together. Now, how do I find points of inflection of a function? Points of inflection are found at the critical numbers, or the critical values of f prime of x. So how do you find critical values of an original function? You take its derivative, you set it equal to 0. Well, this time, if we want to find points of inflection, we're going to set our derivative. Now we're going to find our second derivative, set it equal to 0, and that'll give us our critical values of my f prime. So we're going to take this thing and we're going to set f double prime of x equal to 0, or f double prime of x has to be undefined. One of those two things. That's what I'm going to be looking for. Critical values of my first derivative happen when my second derivative is equal to 0 or my second derivative is undefined. All right, intervals of concavity, we're going to find those intervals the same way that we found the intervals when we were doing the first derivative test. So here's an example, my function. Sketch this graph including all your extrema, inflection points and intervals of concavity. I'm going to start with this thing. Let's make this thing a little bit bigger so that I feel like I've got some space to work. Sketch the graph of this function. First thing we should do, let's rewrite this function. How about if we call it 6 times the quantity x squared plus 3 to the negative first? And the reason I'm doing that is because I know I'm about to take a first derivative, and I'm also going to be taking the second derivative, and neither one of them are going to be as pleasant if I have to do quotient rule. All right, before we start, what do we know about this thing? Is this 6 over x squared plus 3, is this thing a continuous function? Does this thing have any vertical asymptotes? If I take x squared plus 3 and set it equal to 0, I won't have a solution, which means this thing has no vertical asymptotes. So that's something for us to kind of file away. This is a continuous function. So let's start it with extrema. How do I find extrema? I take my first derivative, f prime of x. Nice easy derivative, negative 6 quantity x squared plus 3 raised to the negative second times 2x. Clean it up, negative 12x over the quantity x squared plus 3 being squared. Okay, what do we have for critical numbers? If I want to find extrema, I'm going to need critical numbers. So critical numbers, let's see. Critical numbers, we've done this a few times before. X equals 0 from the numerator, and from the denominator, there are none. So we have one critical number. We have one potential maximum or minimum. If we set up our intervals, so interval going from negative infinity to 0, 0 to infinity, we're going to test in f prime. It's going to tell us about our function. Let's make that black. It's going to tell us about our function that we're trying to draw. So, all right, so I've got, let's see. So if I tested a value in this first interval like negative 1, looking at this derivative that we have in red over here to the left, the denominator is always positive no matter what you plug in. So the only thing that's going to matter, if I plug a negative number in that numerator, I'll get a positive result. If I plug a positive number in that numerator, I'll get a negative result. What does that tell us about my original function? Function's increasing in the first interval, increasing in the second interval. What did we just find? We have a function, and the numerator was equal to 0, which means it would be a smooth curve. We just found a relative maximum at x equals 0, and we're going to need to figure out what our y value is. So our y value, let's go back to the original function. 6 over 0, the quantity 0 squared plus 3, 6 divided by 3, my y value would be 2. So far, we have found we have a point 0, 2 that is going to be a relative maximum. So we've got that part straightened out for now. Now, inflection points. So the new thing. We are effectively going to repeat what we just did, except now we're going to do it with the second derivative. So here's where we find our extrema. Extrema are red. Inflection points are going to be blue. Inflection points are going to be blue. So let's find our second derivative. Second derivative. I'm kind of a fan. Well, this derivative isn't going to be quite so much fun. I'm going to guess that a lot of people will like dealing with maybe this version of the first derivative, negative 12x times x squared plus 3 to the negative second. So I'm thinking I'm going to take the derivative of that, and I'm going to do a little product rule. So if we go and do product rule, let's see. So negative 12x being multiplied by negative 2 quantity x squared plus 3 to the negative third times a 2x. So there's the first times the derivative of the second, plus the x squared plus 3 to the negative second multiplied by the derivative of negative 12x, which would be a negative 12. All right, nasty derivative. I know it's not so nice. So I see two terms here. So let's rewrite those two terms so they look like they should. So negative 12x times, it looks like a negative 2, and times a 2x would be, how about a 48x squared over an x squared plus 3 quantity cubed. There's your first term. Plus a negative 12 over an x squared plus 3 quantity squared. There's my terms. Now, if I want to find critical numbers, the only way I can find those critical numbers is I'm going to have to combine those two things. So if I'm going to combine it, let's see, what do we need? It looks like that the common denominator is going to be x squared plus 3 raised to the third power. So in order to create that common denominator, this second fraction, let's see, we're going to have to multiply here by an x squared plus 3, and we'll have to do the same thing to the top. So if I do that, I've got a 48x squared that came from the first fraction, plus, let's distribute that 12 to the x squared plus 3, negative 12x squared minus 36. And if we clean all that up, how about 36x squared minus 36 over x squared plus 3 quantity cubed. Pardon me. And if we do, let's see, what did we end up with here? We end up with, I'm going to take out a 36. So 36x squared minus 1 over an x squared plus 3 quantity cubed. The reason I'm doing that is because I think it's going to make my life a little bit easier finding critical numbers. So my critical numbers from the top, I'll get x equals both plus and minus 1. And from the bottom, for the same reason we didn't find any vertical asymptotes, we won't have any. So intervals. So now here we are. We're going to do the intervals thing again. But this time when we do the intervals, we're looking for intervals of concavity. So when we set our intervals up, use your critical numbers again. Negative infinity to negative 1, negative 1 to 1, 1 to infinity. And notice all of this is in blue compared to the stuff we did above up here, which started out in red because it came from the first derivative. We're looking for something different now. So I'm going to plug this time, I'm going to check for concavity. What's going on with concavity? So we're going to plug this time into the second derivative to tell us about f. So test values we've been through before. Plug in a number like negative 2. If you look at this second derivative, well, pardon me, denominator, again, plug a number in. No matter what, you're going to square it. You're going to add 3 to it. Denominator is always positive, so the only thing that matters is what happens with the numerator. The 36 isn't really going to have an effect. It's the x squared minus 1. If you plug negative 2 in, square it, it's going to be bigger than 1, which means this second derivative is going to be positive in that first interval. What will that mean about my function? My function is going to be concave upward in that interval. Take a number like 0, plug it in the second derivative. Numerator is going to be negative. That's the only thing that matters because denominator is always positive. That means we found that this function is going to be concave downward in that middle interval. And if we plug in positive 2, like what happened when we plugged in negative 2, this is going to be a plus, and my function is going to be concave upward. So what did we find out? We just found out that this function is concave upward in the first interval, downward in the second interval, upward in the third interval. We just found 2 inflection points. We found an inflection point at the point negative 1, we'll find out in a second, and we found another inflection point, I guess I should call it inflection point, at the point 1, I don't know what yet, so we're going to come up with those values. How do we get those values? We go back to our original function, and I'm going to take this thing now, and I'm going to make this a little bit smaller so we can kind of see the whole page as we're trying to create this thing. So if I scroll it up and I look at my original function, 6 over x squared plus 3, if I plug negative 1 in, I'm going to get 6 over a 4, or 3 halves for my y value. If I plug positive 1 in, I'll get the exact same result. So there's another 3 halves. So what did we find on our graph? Well, we had known a little while ago that we found a relative maximum at the point 0,2. Well, now we have also found an inflection point at the point negative 1, 1.5, and positive 1, 1.5. Think about concavity. According to this thing, it's supposed to be concave upward to the left of that pink dot, concave downward in between the pink dots, and concave upward to the right of that other pink dot. And according to the behavior that we found up here in red, we found this function is supposed to increase until it hits x equals 0 and decrease after it hits x equals 0. So if I do this and I create this graph is going to has to be increasing the entire time until we hit this relative maximum. and decreasing the entire time after we hit that relative maximum. So ideally, if we've drawn this graph right, this function to the left of that pink dot, and let me make the pink dot a little bit bigger, to the left of that pink dot, this function should be concave upward. In between the two pink dots, concave downward. To the right of that second pink dot, concave upward. That's a pretty rough sketch of what's going to happen with graphs. So to sum all this up, red, extrema, same thing we've already been doing since almost the beginning of Chapter 3. Blue is what's new. Blue, now you're taking the second derivative, finding its critical numbers, setting up intervals, but this time instead of them telling us about extrema, like happened up here, now it's going to tell us about intervals of concavity, like what happens by that blue asterisk.